Okay, this is a continuation of our bonding part 3 video. We're going to call this bonding part 3B. We have already talked about Lewis structures for covalent bonding, and now we're going to talk about resonance structures and formal charges. Here we go. There are cases for which the Lewis structures do not agree with experimental measurements of bond length and bond energy. The actual structure of the molecule or ion is viewed as a composite or average of a number of Lewis structures that can be drawn. The actual structure is said to be a resonance structure or a hybrid of the contributing structures. The double-ended arrow was drawn to show that the true hybrid structure is a composite of all the Lewis structures. This would be like you, as a child of your parents, has a nose that kind of looks like your mother's nose and also kind of looks like your father's nose, but it's really yours. It is a composite or a mix of your two parents. Your nose does not switch in between your mother's nose and your father's. It is an actual composite or hybrid of your two parents that you have. If electrons can be moved to create a multiple bond using the procedures that we've discussed already, the number of resonance structures is equal to the number of equivalent choices for the location of the multiple bond. Earlier we were saying, I don't know, let's put the double bond on the left or on the right. Now we're going to see that it's actually a mix of all of those. Let's look at this example so you can see what I'm talking about. In writing resonance structures, the following rules apply. The sequence of the atoms in each resonance structure must be the same. That is, the same atoms must be connected to each other in all resonance structures. So, for example, NCOH does not equal HNCO. They are not resonance structures for the same compound. They are structures of different compounds. Only electrons can be shifted, not atoms. So, this has the order HNCO, so this would have to be HNCO, and it's not. All resonance structures for the same molecule must have the same number of paired or unpaired valence electrons. So for example, the third structure written below is not a correct resonance structure because it has an extra electron pair. And actually, one second, the picture here, the one on the left, is not a correct structure. Those two dots on the bottom shouldn't be there at all, so take those off. And now let's compare the structures. We have 2, 4, 6, 8, 10, 12, 14, 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So 18 electrons for the structure on the far right, and 16 electrons for the two structures in the left and the middle. So the one on the far right cannot be a resonance structure of the other two. Resonance structures usually obey the octet rule, and to determine the bond order in resonance structures, divide the number of bonds by the number of bond locations. I'll get to that in more detail in just a second. Okay, so let's try drawing resonance structures. It goes along the same rules as Lewis structures. Sulfur has 6 valence electrons. Oxygen has 6 valence electrons times 3. 18 plus 6 is 24 electrons is what we should be looking for. So a sulfur with 3 oxygens. That is my skeleton structure. Give everybody a lone pair. Then count up what you have. This is 8, 16, 24, 26. That is too many electrons. So what I'm going to have to do is take a pair off the sulfur and off one of the adjacent oxygens. And it's hard to pick which adjacent oxygen. So for the moment, I'm going to pick the sulfur and the oxygen on the left and give it a double bond. That's one possible way to draw it. But I just as easily, let's see, could have done the bond on the bottom. Or I could have done the bond on the right. And in actuality, it's a mix. The true structure of the molecule is an even mix between the three. It doesn't transfer back and forth between the three. It's an even mix between the three. So the bond order here, there are 3 possible locations for the bond, but there are 4 bonds total. 4 over 3 is 1 1/3. So each of these bonds in actuality is the length and strength of a 1 1/3 bond, which is a little bit shorter than a single and a little bit longer than a double, or a little bit less energy to break than a single, a little bit less energy to break than a double, a little bit more energy to break than a single. Each of these bonds, each of these pictures represents 1/3 of the actual SO3 molecule. Let's look at HNO3. H is 1, N is 5, 3 times oxygen, 18 plus 6 is 24 electrons. Remember, nitrogen goes in the center, the oxygens go around it, and the hydrogen picks an oxygen. Now I'm going to give everybody an octet. And then count them up. So that's 8, 16, 18, 20, 22, 24, 26. 26 is too many electrons. We're going to have to take away two pairs from adjacent atoms and make a double bond. Now, it is not equivalent to put a double bond right here because that oxygen already has 2 bonds. So instead, when I'm picking, I'm going to pick the nitrogen with one or the other of the oxygens that it's not bonded to. So let's start with the nitrogen and the oxygen on the right-hand side and give that a bond. So that would be a resonance structure. Another resonance structure has the atoms arranged in the exact same place. Do not move the hydrogen to a different one of the oxygens. But now we're going to put the double bond on the bottom instead of on the side to make an equivalent resonance structure. It is not equivalent to put the double bond between the oxygen with the hydrogen. So the actual resonance structure is a mix or a hybrid of those 2 pictures. Each of these bonds is not a single or a double. Each of these bonds in actuality is a 1.5 bond or a 1.5 bond order. Next thing we got is formal charges to evaluate whether or not you have drawn a correct molecule when there seems to be multiple possibilities. Calculate the formal charge on each atom in the molecule. The Lewis structure with the lowest formal charges is the most preferred arrangement of the atoms. To determine the formal charges, relatively simple process, determine the number of valence electrons for each individual atom, determine the number of electrons assigned to each atom. Lone pairs count as 2, bonding pairs only count as 1 electron. The difference between the assigned and valence, in other words, assigned minus valence, is the formal charge. Let's see an example. Okay, we've already drawn CO2. Earlier in your notes, maybe rule 4. So I'm just going to take that picture that we already did. That was 4 plus 6 is 16 electrons. We had an OCO with lone pairs looking like this. And 16, that gave us 20 electrons, so we had to take off some pairs. So we took off one from this carbon and one of the oxygens and replaced it with a line. And then we had to decide where we were going to put the other bond. So remember we were saying, should we put a triple bond here or a double bond there? Which one should we do? So if we actually move it to put a double bond there, we're going to calculate the formal charge. Or if we chose the other path and put a triple bond with the oxygen and left a single bond with the other oxygen, we're going to calculate that formal charge and see which one ends up better. So the formal charge is, count the number of valence electrons. Carbon has 4 valence electrons. Count how many are assigned to the atom. A bonding pair counts as one only. So this is 1, 2, 3, 4. Carbon has 4, carbon has 4. This is a 0 formal charge on the carbon. We're totally fine. Okay, so let's look at oxygen. The lone pair count, oxygen's in group 16, so oxygen should have 6. This is 2, 4, 5, 6. Remember, a bonding pair counts as only 1. So oxygen should have 6. Oxygen does have 6. This is a 0 formal charge. The oxygen on the other side, we've got 1, 2, 3, 4, 5, 6. It's supposed to have 6. That's a 0 formal charge. That's a really nice picture. All the formal charges are 0. Let's look at the other picture. For the carbon, again, carbon has 4 valence electrons, and 1, 2, 3, 4. So 4 valence electrons, 4 bonding pairs. That is a 0 formal charge for the carbon. Oxygen, on the other hand, is supposed to have 6. It's got 2, 3, 4, 5 here. So assigned 5 minus valence, what it's supposed to have, 6, is equal to -1. If we look at the other oxygen, we've got 1, 2, 3, 4, 5, 6, 7. Assigned 7. Supposed to have 6. 7 minus 6 is +1. So the oxygen on the left has a -1 formal charge. The oxygen on the right has a +1 formal charge. And even though those cancel to make a neutral overall molecule, it is not the preferred molecule because we could have something that has zeros all across the board rather than a -1, +1, 0. So this guy is out. Let's look at HClO. When we were talking about the rules, 1 plus 7 plus 6 is 14 electrons. When we were talking about the rules, we said H goes with O, not Cl. Let's see what happens when we make it HClO, like we kind of want to do, because that's the order that it's written in. So it's supposed to have 14 electrons, and both of these pictures have 14 electrons. So both of these pictures seem like they should be equally valid. But if we look at the formal charges, hydrogen's supposed to have 1. It has 1 bond, so it does have 1. Assigned minus valence is equal to 0. Hydrogen is 0. Oxygen is supposed to have 6, because it has 6 valence electrons. We have here 2, 3, 4, 5, 6. Oxygen has a formal charge of 0. Chlorine is supposed to have 7 because it has 7 valence electrons. We here have 2, 4, 6, 7. Chlorine has a formal charge of 0. Everybody's great. But if I did it the other way, HClO, hydrogen's still 0. 1 minus 1 is fine. Chlorine, on the other hand, it has 7 valence electrons, but in the picture, 2, 3, 4, 5, 6, assigned only 6. 6 minus 7 is equal to -1. Oxygen, 1, 2, 3, 4, 5, 6, 7. There are 7 assigned. Oxygen is supposed to have only 6. 7 minus 6 is equal to +1. And even though those cancel out to give a neutral overall molecule, we still have formal charges that are further away from 0. So we'd really, really like this picture because we have formal charges of 0 across the board, and we don't really want the other one because we have formal charges of 0, -1, and +1. So formal charge is really just a way to evaluate which of 2 pictures or which of 2 arrangements of molecules is actually more likely to occur in nature. Okay, that's all I've got about resonance structures and formal charges. We'll see you next time for VSEPR.